Okay, guys, good evening. Let's do the chapter 20 homework. Notice it says it's past due, but as I've told you before, that doesn't matter. We can still go in and work the assignment and earn our points for it. Once again, I'll remind you, don't forget to click here and here to get these 2 points, but let's dive straight into the questions. So, for each of the given situations, we want to write the null and alternative hypotheses in terms of parameter values. So a casino wants to know if its slot machine really delivers the 6 in 100 win rate that it claims. So the default is the claim. 6 out of 100 is the proportion of wins. Now notice that I can take that fraction, 6 out of 100, and I can reduce it to lowest terms. But I don't know if it's going to require me to do that, right? But the population parameter is equal to the claim of 6 out of 100, which is 0.06. Now, we want to know if it really delivers that. In other words, we think it might be lower. That's the implication of that statement. Right? Because if the slot machine were paying more, we wouldn't be unhappy about it, right? So our alternative would be that the population parameter is more than the 0.06 value. Really, it's going to do a does not equal. I don't agree with that. It should be less than, but okay, whatever. So it didn't specify one way or another in the wording of the problem, which is why it's asking for a does not equal, but given the context, that's why. Okay, so a pharmaceutical company wonders if its new drug has a cure rate different from 41% rate reported for the placebo. All right, so our reported rate is equal to the 0.41. We want to know if it's different from, so that would be that the proportion is different from. Notice that every single one I'm choosing is the P and not the P hat. The P hat is for the sample. The P is the population parameter. A bank wants to know if the percentage of customers using its website has changed from the 38% that used it before their system crashed last week. So the population was 38%. Now the population may not be 38%. By the way, this is another one that I'd say if people were stopping using the system because it crashed, then that we would suspect it would be lower. So I don't agree with this two-sided again. We would be doing it one-sided, but they're going to want two-sided. So we go with that from the beginning here. Which of the following are true? Okay, a very high p-value is strong evidence that the null hypothesis is false. All right, that's not true because first of all, we're looking for a low p-value, and that's a false statement, right? So, okay. But we're not proving the null hypothesis true. All right. A very low p-value proves that the null hypothesis is false. No, this statement is false. But that's not the reason why. It's not because a high value proves it. A high p-value shows that the null hypothesis is true. This statement is false, not because of that, but because we can't ever prove the null hypothesis is true. A p-value below 0.5 is always considered sufficient evidence to reject a null hypothesis. That's not true. So this one's the closest one. The statement is false because a very high p-value is strong evidence that the null hypothesis is true. Really? Oh, I didn't read that. C. I completely misunderstood this question. I was matching their A, B, C, D here. Teach me. Okay, I was sleeping. This was all about the first statement. I didn't read it that way. I was thinking each of these different statements. I apologize, guys. So yeah, that should have been true. I was associating it with this, not with this. Okay, so that's why that one's messed up. All right, so now we're on this second statement. I understand what's going on here. Man, this homework sometimes is not set up very well. A very low p-value proves that the null hypothesis is false. Okay, we cannot prove that it's false. It just gives evidence that it's false. So that would be D, right? A very low p-value only shows strong evidence that the null hypothesis is false. All right, now C. A high p-value shows that the null hypothesis is true. So this is a correct statement, right? It's consistent with the null hypothesis, but we can't prove that it's true. All right, and now we're on D. A p-value below 0.05 is always considered sufficient evidence to reject a null hypothesis. No, we know that that's not true. It depends on where we set the alpha value, right? Here we go, below the value of alpha, which may not necessarily be 0.05. Okay, which of the following are true? Now, this time I'm reading it correctly. We're only looking at the first statement. A very low p-value provides evidence against the null hypothesis. Actually, yeah, that is true. A high p-value is strong evidence in favor of the null hypothesis. Yeah, actually, that's true. Let's check. There we go. A high p-value merely means that the data are consistent with the null hypothesis. That would be correct. In other words, because I can't ever prove the null hypothesis is true. It's just, it's in keeping with the null hypothesis. All right, now let's look at C. A p-value above 0.1 shows that the null hypothesis is true. No, that's not the case. No p-value ever shows that the null hypothesis is true. That's right. And then D. If the null hypothesis is true, you can't get a p-value below 0.01. That's false. Below this about once in 100 times. That's true. So remember what the p-value is representing. The p-value is how often you expect that result to occur given the null hypothesis is true. 0.01 would be 1 time out of 100, right? So that should be correct. Okay. We want to determine whether it's type 1 or type 2 error. A bank wants to know if the enrollment on their website is above 30% based on a small sample of customers. They test the null hypothesis, p equals 0.3 versus the alternative p is bigger than 0.3, and reject the null hypothesis. They later find out that actually 28% of their customers enrolled. Choose both 4. Okay. All right, so remember what we did in the slides. We kind of made a little diagram here, right? And over here we said, right, here's the actual truth up here. That either the null hypothesis is either actually true or that the null hypothesis is actually false, right? Now, we don't actually know which is the case, right? But it's got to be one of the two, right? Because this is basically saying either 30% of people or above 30% of people use the bank. It doesn't know, it's one or the other. There's no fluctuation about it. The true value is some true value, okay? So either it's 30% or it's not. Now, over here, we do what the test tells us. If the test says the null is true, or the test may give us that the null is right, rejected, right? Or this would be fail to reject, right? Fail to reject. All right, so if I fail to reject the null when the null is actually true, that's a correct thing to do. And if I fail to reject the null when the null is actually false, I've made an error. If I reject the null when the null is actually false, that's the correct thing to do, right? And if I reject the null when the null is actually true, that's an error. So these are our type 1 and type 2 errors. If we recall, this is our type 1 error. This is our type 2 error. Our type 1 error is when we reject the null hypothesis when it's really true. And the probability of doing a type 1 error is alpha. That's why we set the significance level at that point. That's saying, if I say alpha is 0.05, we're saying I'm willing to accept that 5 times out of every 100 I run this experiment, I might accidentally reject the null when it's really true, right? The other one, the type 2 error, really, remember I told you in the slide, is a little bit more complicated, right? But it's the same idea. I fail to reject when it's actually false, okay? So let's see what's going on here. So a bank wants to know if the enrollment on their website is above 30%. They reject the null, so we're in this category, right? They later find out that the null was actually true. That's a type 1 error. The actual value is not greater than 0.3, but they rejected the null. So close to 0.3. Let's see. We're going between not greater than 0.3 or actual value is close to 0.3, but they rejected the null. Okay, so it should be this one. The first one we said, I wasn't sure whether they wanted the value is close to 0.3 or whether it's not greater than, but it's the opposite of this statement here, so it's not greater than. All right, now, a student tests 100 students to determine whether other students on our campus prefer soda brand A or soda brand B and find no evidence that preference for brand A is not 0.5. Later, a marketing company tests all students in campus and finds no difference. Okay, wait, so finds no evidence that preference for brand A is not 0.5. Wow, that's worded poorly. Finds no evidence that preference for A is not 0.5. So in other words, she said it's 50-50. Later, they say it's 50-50. So the student did not make an error. So it should be A. I think I'm going to have to clear this so that we can read a little bit better here. But remember that the type 1 is rejecting the null when the null is actually true. Type 2 is not rejecting the null when we should have. A human resource analyst wants to know if the applicants this year score on average higher on their placement exam than the 52.5 points the candidates averaged last year. She samples 50 recent tests and finds the average to be 54.1 points. She fails to reject the null that the mean is 52.5. At the end of the year, they found that the candidates had a mean of 55.3. Okay, so they are actually bigger than the null, but we failed to reject the null when we should have. That's a type 2 error. So the actual value is 55.3 points, which is greater than the 52.5. Right. A pharmaceutical company tests whether a drug lifts the headache relief rate from the 25% achieved by the placebo. They fail to reject the null hypothesis because that is our p-value. Further testing shows that the drug actually relieves headaches in 38% of people. Okay, so the 38% is more than the placebo of 25. So I failed to reject the null when I should have. The null is actually false. That's a type 2 error, right? The null hypothesis was not rejected, but it was false. The true relief rate is greater than 0.25. In each of the following situations, is the alternative hypothesis one-tailed or two-tailed? A soda company recently reformulated their Diet Cola in an attempt to appeal to teenagers. They ran a taste test to see if the new formula appeals more. So that's bigger than, that's one-tailed. So our null is that the approval of the new one is the same as the approval of the old. And our alternative is that the approval of the new is now greater than the approval of the old. All right, a budget override in a small town requires a 2/3 majority to pass. A local newspaper conducts a poll to see if there's evidence it will pass. I've got to be bigger than 2/3 to pass. So that's one, that should be one-tailed. All right, so the voters for the budget equal to, or actually is less than. Well, equals, we can always do equals for the null, and then greater than for the alternative. Actually, that should be greater than or equal to. Because it passes at 2/3 majority. So this should actually be greater than, and this should be less than. I don't know if it'll let me take that or if it wants that equal there. Let's check it. Nope, it wants the equal there. So equal there, and then we would have to do strictly greater than here. Again, the equal to really should be here based on the way this is phrased, because it requires a 2/3 majority to pass. All right, part C. One financial theory states that the stock market will go up or down with equal probability. A student collects data over several years to test the theory. That's two-tailed because it's going up or down with equal probability. The probability that stocks go up is equal to the probability stocks goes down, and does not equal for the alternative because this is a two-tailed test. A medical researcher tested a new treatment for poison ivy against the traditional ointment. He concluded that the new treatment is more effective. Explain what the p-value of 0.009 means in this context. If there is a difference in effectiveness, the chance of seeing an observed difference this large or larger is 0.9% by natural sampling variation. That sounds correct. What's the difference here? Let's see. Oh, if there is a difference versus if there is no difference. Should be if there is no difference in effectiveness, right? If they're really the same, the chance of getting this by sampling error alone is 0.9%. A researcher developing scanners to search for hidden weapons at airports has concluded that a new scanner is significantly better than the current one. He made his decision based on using a test using alpha equals 0.05. Would he have made the same decision at 0.2 or 0.001? Okay. All right, so notice that this is saying we think our new scanner is better, so it selects more than the current scanner. So this is going to be a right-tailed test because the selecting more than would be a bigger, right? So this is one-tailed. And he used an alpha of 0.05, so this is the 0.05. So he concluded his is better. So his sample mean's over here somewhere, right? Whereas the standard mean is over here. Okay. So now his decision would have been the same if alpha equals 0.2. Well, if this is an area of 0.05, an area of 0.02 would be over here, right? All of this. So yes, he would have made the same decision for this, right? But the area for the 0.01 is less than 0.05. So maybe just this portion of area. And I don't know whether this point actually fell here or it fell over here. I have no way to know. So his decision might have been the same for this, but it might have been different. It definitely had to be the same for the 0.2. So his decision would have been the same for alpha equals 0.2, but may have been different for 0.01. Public health officials believe that 90.1% of children have been vaccinated against measles. A random survey of medical records at many schools across the country found that among more than 13,000 children, only 88.1% have been vaccinated. A statistician would reject the 90% hypothesis with a p-value of 0.022. Explain what the p-value means in this context. Okay. If 90.1% of children were really vaccinated, the probability that we would have come up with 88.1% in our sample would have only happened 2.2% of the time, right? So there is a 2.2% chance of seeing a sample proportion as low as 88.1% by natural sampling variation if really 90% have been vaccinated. The result is statistically significant, but is it important? Why? Okay. Yeah, this should be just this is statistically significant because the p-value is low. So our results should be important. Okay, here we go. Okay, a 2% drop would probably not be considered noteworthy, but in context, if 1 million children are vaccinated each year A 2% difference accounts for 2,000 more children not being vaccinated, which is important. Okay, I see. This said all statistically significant results are important. All right, I understand what they're doing now. I'm sorry, that took me a second. It is not true that everything that is statistically significant is important, right? So, okay, you got to look at like the context of the problem. For example, if I were to, you know, I don't know, look at the grade distribution of blue-eyed people, right? And I saw that, you know, blue-eyed people had a statistically significant 1% lower score on tests than brown-eyed people, right? Well, in the context, that is absolutely meaningless. My eye color doesn't affect your performance on a statistics test. So even though that might be a statistically significant result, it doesn't actually mean anything. So the problem here is the word all, right? So we don't want to use word all. So here, even though it's not a huge jump from 90 to 88.1, it's a 2% jump. That is still 2,000 children. That's significant. All right. Before lending someone money, banks must decide whether they believe the applicant will repay the loan. One strategy is to use a point system. Loan officers assess information about the applicant, totaling points they award for the person's income level, credit history, credit debt burden, and so on. The higher the point total, the more convinced the bank is that it's able to make a safe loan. Any applicant with a lower point total than a certain cutoff score is denied a loan. We can think of this decision as a hypothesis test, since the bank makes its profit from the interest collected on repaid loans. Their null hypothesis is that the applicant will repay the loan and therefore should get the money. Only if the person's score falls below the minimum cutoff will the bank reject the null and deny the loan. Okay, all right. So the null here our null here is that they get the loan. So the alternative is that they don't get the loan. So if we determine that they should get the loan when they're really going to default on it, so we're saying that we're not rejecting the null. So we are failing to reject the null if we give them the loan, but we really should have rejected the loan. That's a type 2 error. Which kind of error is it when the bank misses an opportunity to make a loan? So they rejected the null when they shouldn't have. That would be a type 1 error. Suppose the bank decides to lower the cutoff score from 250 points to 200. Okay, that would be equivalent to choosing a lower value of alpha. You're making a more stringent criteria. Wait a second, hold on, no. Our null is that they are given the loan. The alternative would be that we don't give them the loan. So if I make it harder not to get the loan, that would be equivalent to lowering the alpha. Because we're lowering the cutoff score from 250 to 200. So we should be rejecting less people. That would be a lower alpha level. What impact does this change in the cutoff value have on the chance of each type of error? So I'm decreasing the probability of making a type 1 error. So decrease type 1, and we're going to increase the probability of making a type 2 error. We're going to increase the probability that the person defaults on the loan because we're giving them a lower cutoff score. Before lending someone money, okay, this is the same thing. Yeah. What is meant by the power of the test? All right. So your power of the test, remember, is the ability to make that correct decision, make that correct rejection. So the power is that we approve a loan that would be repaid. Okay, we said the null hypothesis was that we give a loan. The alternative hypothesis is that we reject the loan. So this is the probability that the bank denies a loan that would not have been repaid. I think, okay, all right. Now, what could the bank do to increase the power? All right, our probability that we deny a loan that would not have been repaid. So to increase the power, we would lower the cutoff score because then we're only taking the worst applicants, taking just the worst applicants, and only those are the ones we would be rejecting. We're more likely to only reject the ones that would not have been repaid. All right, so let's see what we messed up here. Increasing alpha. Lowering the cutoff score would decrease the alpha. We should raise the cutoff score. Yeah, okay, I'm sorry. I said that backwards. I read it correctly, but I said the wrong thing, lowering it and getting only the ones that don't default. That's not what we're going for. The higher I make the cutoff score, the more likely I'm going to catch everybody who doesn't default. And that's what we would do, right? That would increase the power. Okay. What is the disadvantage of doing that? Well, we'd also end up telling a lot of people who would repay the loan that they can't have the loan, right? A larger number of trustworthy people would be denied credit and would miss the opportunity to collect interest on those loans, right? In other words, we would end up not lending to a lot of people who would have repaid us because we made the cutoff score too high. A statistics professor has observed that for several years, about 14% of the students who initially enroll in a stats course withdraw before the end. A salesman suggests that he try a statistics software package that gets students more involved with computers. The professor can use the software free of charge. Initially, 176 students sign up for the statistics course. They used the software suggested and only 15 dropped out of the course. Okay, this is one-tailed because he thought using the software would decrease the dropout rate. So our null is that we drop out at a rate of 14, so it should be P equals 14. So here, here, here. We think we're decreasing it, so the alternative would be that we go lower. A type 1 error. All right, so my null is that there's no change in the percentage you drop out. It's still 14%, right? So a type 1 error would be when I reject the null hypothesis, but the null hypothesis is really true. So I believe that software lowered the dropout rate, but the dropout rate really stayed the same. So the professor buys the software, but the dropout rate has not actually increased. All right, so a type 2 error would be we don't buy the software, but it really would have decreased the dropout rate, right? What is meant by the power of the test? The power is the probability that the professor buys the software when the dropout rate has really decreased. Okay. So this is the same question. All right. No, I'm sorry. All right, so 10% who initially enroll in the class withdraw before the end. We're trying a software package again. Okay, so we're using alpha equals 0.05. A 186 is less than 10% of all students who have taken the class with the professor. And these are representative of students. So we know we can run our statistical test. So our hypotheses are that we equal 0.1 and that we're going lower than 0.1. So that's here. Compute the test statistics. So let's get our calculator out here. Fun. There we go. All right. So, man, everything's in the way here. Hold on, I'm sorry, I gotta stop sharing so I can move the calculator out of the way because I can't move it with that. All right, sorry, I apologize for that. Let's share the screen again. Okay, there we go. All right, so we are doing a stat tests, 1 proportion z test, option 5. Our P naught is the 0.1. The number that dropped out is 15 out of the 186. Yeah, 186 is our N. We hypothesize that we're less than, so let's calculate it. Our test statistic is 0.879, so we'll run that to 0.88. Oh, I missed the negative sign there. I'm sorry, negative 0.88. Calculate the p-value. So our p-value is this probability right here, 0.1, 4 decimal places. So here, 0.1895. Oh, there we go. Should the professor spend the money for the software? All right, well, notice we were testing at alpha equals 0.05. This is bigger than 0.05. So since it's bigger, we're not going to reject. We're going to fail to reject the null hypothesis. So if we fail to reject this, we're saying we didn't really see a change from the 10% dropout rate. So no, we should not buy the software because the p-value is greater than alpha. We do not reject the null and conclude there's no strong evidence that the dropout rate has fallen. Explain what the p-value means. The chance of observing 15 or fewer dropouts in a class of 186 is 18.95. I just moved the decimal over 2 places to convert to the percentage. If the dropout is really 10%. It's not more than. Alrighty. Okay, that completes our homework. So you guys should be able to do all of this. We're going to stop here. Let me know if you have any questions.